Shall we start now? शुरू कर दी everyone?
Sir, sorry.
अच्छा. Something very very highly interesting thing is going to happen.
Also, sir.
हाँ.
বলছি যে নেক্সট ডিএনএফ ব্লক কারেক্ট হবে রাইট?
হ্যাঁ.
কবে হবে?
একটু দাঁড়া, আগে করতে দে, মাথা কেটে যাবে আমার. Horizontal trend in ionization enthalpy of 3D elements. We are majorly going to focus on the 3D elements alone. Now you see, when I'm talking about ionization enthalpy, I will ask you to recall the concepts that we studied in 11th standard. That over there we studied that it depends on several factors like Z effective, shielding effect, etc. Here what we are going to do is again similarly effective, নিউক্লিয়ার চার্জ. মৌসুম, তোদের স্কুল থেকে সবাই আছে, মেয়েরা জয়েন করেছে? effective nuclear charge, then next important parameter, electronic configuration in terms of exchange energy. These two terms are going to play a very very vital role in deciding the ionization enthalpy trends. First, if I look at the effective nuclear charge part, then we know usually from left to right, what happens to Z effective, everyone? Increases. So ionization enthalpy should, in general, what should happen to that? Decrease. Now the thing is that the 3D electrons can shield the 4s electrons from the nuclear charge more effectively than the 4s electrons themselves can do. Now it might be misleading, that's why I am giving a perfect clarity of it. Sir, we have been learning that if there is an inner d orbital, it will always exert pore shielding effect and therefore Z effective should increase. True. But that is true when we are talking about non-transition elements. That means n-1d is the inner orbital and the electrons are filling up in the p orbital. Under that scenario, because np and n-1d, they are far away from each other, pore shielding effect of n-1d will affect the Z effective experienced by the p electrons. But here what we are saying is, we are comparing the shielding effect of the s electrons among themselves, and versus shielding effect of d electrons and 4s. So in order to visualize this picture, I am taking a comparison like this. If this is the nucleus I am taking, and if this is the 3d orbital outside which the 4s subshell is present, then what is happening exactly is the electrons which are filled in 3d subshell will be now capable of shielding the nuclear charge more effectively than the 4s electrons can do themselves. That means the effective nuclear charge, or rather I should say the shielding effect, that will be caused by one 4s electron on another 4s electron versus 3d electrons on 4s electrons. Where do you think the effective shielding will be taking place? 4s electrons shielding 4s electron, or 3d electrons shielding 4s electrons? Where, according to you, more effective shielding effect should be present? Correct? No. So for 3d electrons shielding the 4s electrons more effective than 4s electrons shielding the 4s electrons. So why are we getting bothered about it? Because for d block elements, the first electron will be lost from 4s, whatever we do. Now when the electron is lost from 4s, in the beginning we discussed, now we will be discussing about it more in a more deeper way, that once this 4s electron is lost, the energy distribution between 3d and 4s gets disturbed. As a result, we will always think, or we will always do the calculations in a way that we will drop the electron from remaining 4s, if there is any 4s electron remaining after removal of the first electron, then we will drop that 4s electron to 3d to enhance the exchange energy. What am I saying? Once one electron is lost from 4s orbital, obviously during first ionization, the energy distribution between the remaining 4s electron and 3d electrons get disturbed, and the 4s remaining electron is brought down to 3d to boost the exchange energy stability. What does that mean? Let us try to understand that with examples. Let us start with scandium. So scandium was having, what is the electronic configuration scandium was having? Tell me guys. 3d1 4s2. Correct or not everyone? What is the exchange energy right now? You have calculated in the beginning. You check your own copy, you have done that. D1, D2, D3, D4, 5, etc. You have done it. What is the exchange energy against this? 0K. Correct or not everyone?
0K.
Now if I remove an electron from 4s, to obtain scandium plus, obviously gaseous, because ionization enthalpy is always dealt in terms of gases. What am I supposed to get? 3d1 4s1, but I will not do this way. Instead, I will bring down that 4s electron to the 3d electron. I will make it 3d2. So against this 3d2, what is the exchange energy now?
1K.
K, just K, 1K, yes. Everyone keep on responding, everyone. Okay, participate. Or co-participate. Let's say, now let's say I want to remove another electron. So you get scandium plus 2, right? So what is remaining then? 3d1 remaining, correct everybody? Everyone, come on, response. So it is again what? 0K. Let's say you again remove another electron. What do you get? Scandium plus 3 gaseous. What do you get? Basically, it is getting the configuration of argon. Now similarly, we will keep on doing the same process up to zinc. Let us see what happens. So now it is titanium. So what is supposed to happen in titanium? 3d2, 4s2. What is the exchange energy, everyone? 1K, right? With respect to 2d electrons, it is 1K. Can everyone follow that? Just keep on responding, guys.
Yes, sir.
So titanium 2 plus gas, it was supposed to get the electronic configuration 3d2, 4s1, but I will be merging the 4s electron into 3d. As a result, what I will get now? 3d3. What is the exchange energy now then?
3K.
3K. Against 3 unpaired electrons, it will be 3K.
Sir, titanium 2 plus 53 to 4.
I'm sorry. This is plus only. Another electron removed, so titanium plus 2. So it is supposed to be becoming what? 3d2 then? What is the exchange energy now? Again 1K. Can you guys follow? Keep on responding that. Another electron if I want to remove. Titanium plus 3. What is the electronic configuration? 3d1. Exchange energy 0K. Another electron removed. Titanium plus 4 gaseous. Then again, what have I achieved? Inert gas configuration. Correct. Now, same process. Vanadium, let us do what it was. Electronic configuration 3d3, 4s2. What was the exchange energy, everyone? 3K. Can you follow, everyone? One electron removed in vanadium plus gas. What is electronic configuration supposed to be?
3 to 3 4
But it will do what? It will submerge into 3d4. against 3d4, what will be the exchange energy coming?
6K.
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 6K. Now let's imagine to remove another electron from vanadium plus. So vanadium plus 2, how much is it supposed to come then? 3d3. What is the exchange energy?
3K.
It is supposed to be 3K. And the process can be continued accordingly. Same thing, let's say vanadium chromium. What is the electronic configuration in chromium? 3d5, 4s1.
4
What is the exchange energy? 10K. Right or wrong?
Yes, sir.
And chromium plus, if it happens, It is 3d5 only. So again, what is the exchange energy? 10k. If I remove another electron, what do I get?
3d4.
Chromium plus 2 gas if I make, it becomes 3d4. What is the exchange energy then?
6k.
6k, no? If I remove another electron, chromium plus 3 if I form, what is the electronic configuration? 3d3.
3k.
So it is 3k. Let us try to repeat the same thing with manganese. Manganese is supposed to be of what configuration? 3d5.
3d5 4s2.
What is the exchange energy then?
10k.
10k. If I remove an electron, what am I getting? What is the electronic configuration?
3d5 4s1.
But what it will do? It will submerge into one. If it does convert into 3d6, then its exchange energy 11k. 3d6 divided into, hey, who is it? Again. Okay. So as I told you in the beginning that 6 if it is given, then I am supposed to convert it into 5 plus 1. So D5 against exchange energy is 10k and 1 electron. No, not 11k, it is 10k only, because 5 against exchange energy is 10k. 1 against exchange energy is how much? 0k.
0k.
So it is 10k. It is 10k. Can everyone follow?
Yes, sir.
Now, if I remove another electron to form Mn plus 2, what do I get? Electronic configuration 3d5 only, where exchange energy is how much? Again 10k. If I wish to remove another electron, what do I get?
3d4.
3d4. So what is the exchange energy here? 6k.
6k.
Then oh, just a minute. Then after manganese, which one is coming? Iron. Iron is having which configuration, guys? Everyone? 3d6, 4s2, correct or not? Arjudeep, what is it? Tell, Arjudeep, tell. What is it? Arjudeep? So what is the exchange energy in this case? Against D6, what is the exchange energy, everyone?
10k.
10k. Now if I remove one electron, I get Fe plus. What is the electronic?
3d6 for this one.
So it was supposed to be. Can I do a step jump?
Yes, sir. Yes, sir.
Achha, it will create confusion later. So it will convert into 3d7. Now d7 is supposed to be imagined as 5 plus 2. 5 against it is 10k and this is k. Now it is 11k. Can everyone follow? Rishi, Swambu, Satyajit. If I remove another electron, Fe plus 2 gas, what is it? It will be having which configuration? 3d6 then? What is the exchange energy then supposed to be? If I remove another electron and get converted into Fe plus 3 gas.
3d5
No, in the beginning, as we discussed, that in D6, due to one extra pairing, there is a pairing energy. Due to extra pairing, the energy is higher than 3d5. Everyone is joining in some. Till here, clear for everyone?
Yes, sir.
Then after iron, it is coming cobalt. So what is it? 3d7, 4s2. Now the exchange energy 7 means Oishik tell.
স্যার বলছি আমরা যে এনার্জি লেভেলগুলো কম্পেয়ার করছি এগুলো কিসের জন্য একবার বলবেন? আমি জাস্ট জয়েন করতে লেট হয়েছিল।
Ionization energy we will be doing on the basis of this.
Just comparing the energy levels of different plus charges.
Yes.
After removing the electrons.
Yes.
Okay, sir.
So it is 5 plus 2. That means it is supposed to give me 11k. From there, if I remove one electron, get cobalt plus, that will become, or that is supposed to become 4s1 3ds 4s1, but that will submerge into 3d8, which is supposed to give me 5 plus 3, so that is 13k. If I remove another electron and achieve cobalt plus 2, what will I be getting? 3d7. So that is going to give me what? Exchange energy of 11.
11k.
If I do the same with nickel, if I take nickel, it is 3d8 4s2. If I remove one electron, nickel plus I form, it is 3d8 4s1. Nickel plus 2 if I form, it will remain 3d8. Here I will try to make it 3d9, that is 16k. Here it is supposed to give me 5 plus 3, that is 13k. Clear for all? And again here it is 13k. Then if I wish to do for copper, so let's say copper, it is 4s0 3d10 sorry 4s1 3d10. So if I remove one electron, it becomes 3d10. 3d10 means 20k, and here it was also 20k. If I remove If I remove another electron from copper plus, it will become 3d9, which will count as exchange energy to be 16K. Last but not the least, we should count, that is for zinc. We should count for zinc. Let's say zinc plus, zinc 2 plus. So zinc means it is 3d10. It is 10, so it will have to remain 10 only, because it is already filled. I cannot change it. So here it is 20K, here it is 20K, here it is also 20K. Correct or not? So exchange, in terms of exchange energy, nothing is getting disturbed or nothing is getting changed. Clear for all?
Yes, sir.
Now you see, as from scandium up to zinc, normally what should happen to the effective nuclear charge? Starting from scandium up to zinc, what should normally happen to the effective nuclear charge? It should increase. Now you see, what are we experiencing in every cases? In the case of scandium, let's say, scandium to scandium plus, loss of if I say gain of in a way, Moitri is already there in the class or not?
Yes, sir.
No, N2 Moitri. N2 Moitri, not school Moitri, another one. Or go school toder Moitri ki ache class already. Lata, Shorupa, Shornali, is Moitri already there in the class? हाँ, Moitri नहीं ना?
No, sir.
Okay. Is it really Moitri? Please, can you confirm, Shorupa, who have joined just now? ওটা সত্যি সত্যি মৈত্রী কিনা একটু জেনে দেখে নে তো। Now, from scandium plus to scandium 2 plus. This is first ionization energy. This is second ionization energy. Now, why during the first ionization energy, I am gaining exchange energy or losing exchange energy? During the first time, am I gaining or losing? Gaining, no? Because it was earlier 0K, now it has become 1K. So I have gained some stability. So I will, in terms of exchange energy, in terms of gain in exchange energy, I can say it is plus 1K. And to scandium 2 plus, I have again lost exchange energy, no? So it is minus 1K. That means scandium plus, it was exchange energy 1, to scandium 2 plus, it has become 0. Can you follow?
Yes, sir.
Similarly, with the similar argument, titanium to titanium plus to titanium 2 plus, if I look, first ionization energy, second ionization energy, what is the gain in exchange energy? 1K to 3K, what is the gain?
Okay.
3K. And second time, lost, minus 2K, lost, exchange energy loss is happening. Then again in terms of vanadium, if I go for it, vanadium to vanadium plus 2, It is first ionization energy, second ionization energy. During first ionization energy, am I gaining exchange energy? If yes, then how much? 3K. It is increasing by 3K. 3 unit stability is increasing. And followed by second time losing by 3K. Can you follow everyone?
Yes, sir.
From chromium to chromium plus to chromium 2 plus, what is happening? This is the first ionization energy, second ionization energy. What is happening to the first ionization energy during the first ionization energy? 0K. 0K, no change. And then it is losing stability by 4K.
Minus 40.
Then when I am going to third ionization energy to get chromium plus 3, then what am I getting? Exchange energy. Gain in exchange energy is by how much? 6K to 3K. Correct or not everyone? Minus 3K. Orko Prabhu, are you already there in the class?
Yes.
Huh? Yes, okay. Similarly, manganese to manganese plus to manganese plus 2 to manganese plus 3. First ionization energy, second ionization energy, third ionization energy. So gain in exchange energy in the first time, what is it? How much is it? 0. During the third time, manganese plus 2 manganese plus 2 थे
0.
manganese plus 2 manganese manganese plus 2 to manganese plus 3
Minus 4.
correct. In terms of iron, now if I want to investigate similarly, iron to iron plus to iron plus 2 to iron plus 3.
First ionization energy plus 1.
First exchange energy gain is how much? Yes, tell. 1
Plus
unit.
1.
1 unit. Second ionization energy gain is
Minus 1.
minus 1. Third ionization gain is again
0.
0.
0.
Cobalt to cobalt plus to cobalt 2 plus. First ionization energy, second ionization energy. First exchange energy gain plus 2K. Then again is
Minus 2.
nickel to nickel plus 2 to nickel plus 2. First ionization energy, second ionization energy. So first time exchange energy gain is how much? 3K.
Plus 3.
And during the second time it is
Minus 3K.
right. And similarly we can count for the remaining. I am not going for further. Now after doing the whole process, what are we trying to establish exactly? Let us try to get it with the idea of graph.
So 2 minute technique লিখবো।
এতক্ষণ কি করছিলিস? আমার সাথে সাথে লিখিস নি?
লিখছিলাম, কিন্তু ওটা বেশি পাওয়া যাচ্ছে।
এটা লিখবার জন্য এক্ষুনি টাইম দিতে পারবো না বেটা, পরে দিচ্ছি। নাও স্ক্যান্ডিয়াম, টাইটেনিয়াম, ভ্যানেডিয়াম, ক্রোমিয়াম, ম্যাঙ্গানিজ, আয়রন, cobalt, nickel, copper, zinc, and in this part, in this quadrant, I am putting the ionization energies axis on the y-axis. Now in the general way, as you guys anticipated in the very beginning, tell me once again based on that, if I am moving from left to right, what should I be expecting to the ionization energy value? What should it be happening? It should be happening what? It should happen to what? It should increase only or decrease?
Increase.
So if it is that general expectation from my end or our end that it should generally increase, what exactly are we observing or obtaining from the experimental set? Let us try to observe that first, and then I will ask you guys to explain that observation. Okay? You open your NCERT, everyone, and tell me what can you see the first ionization enthalpy data. I hope everyone can open your NCERTs. You will find it in your table number 2. This is second table in NCERT, DNF. Clear?
Yes, sir.
So, what are we observing? Let us start noting it down. For scandium, please tell me, guide me. 631, 656, 650, 653, 717. See, I don't also remember. I am also referring the NCERT datas only. 758, 736, 745, 906. These are the values given, everyone. Do we agree? Just let me know quickly.
Yes, sir.
Correct? No? No. Now, so if I start putting the lines, scandium to titanium increased, but then titanium to vanadium there is a slight drop in the value. Can you follow that? Can you follow that? Can you observe that? Scandium to titanium there is an increase, but then titanium to vanadium there is a slight drop. Not as less as scandium, but there is a drop. Can you follow?
Yes, sir.
But then to chromium it is again increasing. Lesser than titanium, we are not going to establish the order. Order is very much what should I say, very much random, but we are trying to, and we are going to address the reason behind it. Unlike the P block and S block elements, we are not going to explain sorry, we are not going to follow the order overall, but we are going to understand and explain how is it happening or how possible it is happening. Now chromium to manganese there is a large jump value. Manganese to iron also we can see there is a large jump value, but iron to cobalt very little decrease, almost equal. Nickel, cobalt to nickel there is a slight again declination. Just a minute. Then nickel to copper we can see there is a slight increase again. Copper to zinc at the maximum. So in reality what are we getting is हाँ
745 to 758 থেকে বেশি মনে হচ্ছে।
চেঞ্জ করে দিতে হবে। This is merely a qualitative diagram. We are not going for the exact parameters. Which one are you talking about? 745 is greater than 758, it seems. 745. Now it is okay, I guess. Okay. Everyone, this is the graph that we can expect. Again, I am telling you, we are not going to go for the exact order prediction, but rather we are going to understand on which basis these anomalous points are happening. Anomalous points as we can see from titanium to vanadium, there is a little drop. Then again iron to cobalt, a little drop. Cobalt to nickel, little drop. Can you experience that? On the other hand, we were expecting যে এটা thoroughly left to right কি হওয়া উচিত? What should it have happened? Increase. So basically what is happening is titanium to vanadium, there is a little drop in ionization energy. Then iron to cobalt, cobalt to nickel, there is a little drop in the ionization energy values. Now why is that happening? That we are trying to understand. These all values are first ionization energy values. Now you look at the when scandium to titanium, I mean scandium first if I keep on writing the exchange energy loss during first ionization, exchange energy loss during first ionization, just check the data that we have just now solved. For scandium, how much was it? 1k. It was gain of 1k. Titanium 2k. Vanadium 3k. Can you follow? 1k, 2k, 3k. Can you follow everyone? For chromium, it was 0k. Are you able to follow everybody? For manganese, the exchange energy gain was again 0k. For iron, the exchange energy gain 1k. For cobalt 2k. Nickel, last we did for nickel only, it was 3k. Can you guys follow? And we are not counting any further because for copper zinc it is a usual expected order we are following. আমরা কি বোঝাতে পারছি এটা? ফার্স্ট আয়নাইজেশনের সময় আমার কতটা করে এনার্জি এক্সচেঞ্জ এনার্জি গেইন হয়েছে that we have noted down. Am I making sense to all of you, Odibhan and all?
Yes, sir.
Now you see during this vanadium first ionization process, during this vanadium first ionization process, because it is gaining 3k amount of exchange energy stability, that is the reason the ionization energy is slightly lesser. Then what is happening to the next one, sir? In a similar manner, you see 0 to 1k and 1k to 2k, almost they are in the same amount of stability gain. Almost they are in the same amount of stability gain. This is 1k extra stability it is gaining. I mean, you see, for manganese to manganese plus, there is no extra additional stability gain. Effective nuclear charge is increasing, so that is the reason ionization energy is increasing. But from iron to iron plus 2, exchange energy stability is there. If it is getting Fe plus, it is getting 1k of additional exchange energy, true, but at the same time it is not as overwhelming as with respect to the Z effective. That means Z effective from left to right is trying to increase the ionization energy, and exchange energy gain, if it is happening, then it is trying to lower the ionization energy. Now from titanium to vanadium, Z effective increased, but from titanium to vanadium, gain in exchange energy also increased. Are you guys able to follow what I am trying to say? আমার টাইটেনিয়াম থেকে ভ্যানাডিয়ামে Z effective বেড়েছে, that should definitely increase my ionization energy, but also my from titanium to vanadium exchange energy gain has also increased, and as a result overall what is happening, vanadium is getting a slightly drop in the ionization energy value. Is that clear for everybody? Please let me know. Come on.
Yes, sir.
Yes, sir.
So first what I am writing here is from titanium to vanadium increase in Z effective tends to increase I1 value, but in vanadium upon ionization ,3k amount of exchange energy gain more stability. That is why vanadium to vanadium plus has lower ionization energy than titanium to titanium plus. Orko, have you understood? Orko, have you understood? Orko, have you understood?
One second.
Now the C.
Stability related to
Exactly. So vanadium to vanadium plus A, exchange energy stability 3. हाँ?
Stable जब तो बेसिक तो रिएक्शन जाते हैं आपके बार-बार
अठारह तरीकी स्टेबल का vanadium plus, not vanadium.
अच्छा
Stability
सॉरी बात तो
স্টেবিলিটিটা upon ionization বাড়ছে, not in the neutral atom. Exchange energy gain or exchange energy loss, that we are only looking at. Can you guys follow? Yes or no? Come on, let me know.
Yes, sir.
Clear for all?
Sure, sir.
Next you see, in case of this iron cobalt thing, it is hardly much of a change, but still we should be looking at it. You see 656 to 650, 6 unit drop it was, and here we can see it is a 4 unit drop in ionization enthalpy value. So hardly it is a drop, but at max we can say that in cobalt to cobalt plus it was a 2k amount of exchange energy gain. That's why cobalt to cobalt plus formation is more favorable than the iron to iron plus formation. Similarly, nickel to nickel plus formation is gaining 3k amount of exchange energy, so it is more favorable than cobalt to cobalt plus formation. Can you guys follow?
Yes.
So you see, nickel to nickel plus exchange energy gain is 3k which lowers first ionization energy of nickel than cobalt, in which iron brings exchange energy gain of 2k. Also, cobalt to cobalt plus ionization energy is lower than iron to iron plus, where gain in exchange energy is only 1k. Just tell me, have you understood this or not? Otherwise, you see, throughout the whole series, it is increasing pattern. Scandium to titanium, titanium to vanadium, vanadium to chromium, manganese and everything, it is increasing. But only titanium to vanadium, little drop. Iron to cobalt, cobalt to nickel, drop. First ionization energy trend follows like this. Just let me know if you have understood this or not. Quickly, just let me know.
Yes, sir.
Now, look at your that table 2 for second ionization enthalpy data. Just confirm with me, guys. It is 12. It is 12:35, 13:09, 14:14, 15:92, 15:09, 15:61, 16:44, 17:52, 1958, ionization enthalpy na পলাশী যুদ্ধ, হ্যাঁ, 1734. Now you see, okay, first thing you observe and tell me, obviously first ionization energy to compared to second ionization energy, it will increase. Second ionization energy to third ionization energy, it will also increase, because we know successive ionization energies always increases. Correct, Shamashri, Neha, Mosam, Shamadrita,
Yes, sir.
Jinia,
Yes, sir.
Mishra. Now,
Yes, sir.
now, but the surprising part is, you see here the gaps, the variations. Can you see that? Apart from zinc, which is fully filled configuration, if I leave that part, the adjacent values are changing by how much? Maximum 20 units. Can you observe that?
Yes, sir.
During the first ionization energies values for the back-to-back elements or consecutive elements, the first ionization energy is increasing or varying or changing very little. But that, if I look at here, it is changing 100 units. Approximately 100 units it is increasing or changing. Do you follow that? Shavarika, can you tell me? Do you follow that? Come on, confirm it, quick.
Yes, sir.
মানে আমার এখানে সেকেন্ড আয়নাইজেশন এনার্জি চেঞ্জটা is much more prominent or much more drastic as compared to the change in the first ionization energy values. Do we agree on this or not? Now you see from here to here, now from here to here increased, 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 then decreased, then again increased, 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 decreased. Can you follow that? If you can follow the trend, just let me know quickly.
Yes, sir.
Correct, no?
Yes.
How do we explain that? Left to right, usually what should happen? Or go left to right, Z effective, what should happen to that?
Increase.
So,
Increase.
so what is the usual thing that has happened? The drop one or the increase one? Increase হওয়াটা usual ছিল না drop হয়ে যাওয়াটা usual?
Increase.
Increasing drop is the anomaly. Dropping is the anomaly. Correct, no? Now how do I explain that? Gain, exchange energy gain or loss? Correct or not? Everybody? During second ionization energy, sorry. Exchange energy gain, exchange energy gain during second ionization energy. Tell me for scandium how much was it, everyone? For scandium what it was? How much? Minus 1. For titanium?
-2.
Everyone please have a look. When we will be noting it down, you just guide me there. Otherwise I have to shuffle again and again. For vanadium?
-3.
For chromium?
Zero.
Huh? Loss in exchange energy or gain? -4. For manganese?
Zero.
Okay, till manganese let us note it down. So it is -1K, 2K, 3K, 4K. For manganese how much was it?
0.
You see, exchange energy is lost, losing, becoming negative. So that's the reason, if it is losing exchange energy, if it is losing the stability in terms of exchange energy upon ionization, what should you expect about the ionization enthalpy value? Should it be decreasing or should it be increasing, Jinia? যদি আমার আয়নাইজেশন হওয়াতে এক্সচেঞ্জ এনার্জি লস হয়, তাহলে should I be expecting increase in ionization enthalpy or decrease in ionization enthalpy?
Increase, কারণ Z effective থেকে enter করছে না।
Correct. That means that is the reason you see scandium to titanium increase, titanium to vanadium increase, vanadium to chromium increase. But then all of a sudden manganese decreased. Why so? কারণ এখানে exchange energy loss নেই. Can you follow everyone?
Yes, sir.
অনির্বাণ, ঐশিক,
Yes, sir.
কারণ আমরা এখানে এক্সচেঞ্জ এনার্জি লস হলো না। প্রাঞ্জল বুঝতে পারলি কি পারলি না? অর্চিতা বুঝতে পারলি কি পারলি না? কারণ আমার এখানে কোনো এক্সচেঞ্জ এনার্জি লস হলো না। তাহলে আমার কি হচ্ছে এখানে দেখো, from scandium to chromium during second ionization exchange energy loss is increasing gradually. That's why नेहा मौसम শ্যামাশ্রী এটা বুঝতে পারলি কি পারলি না? That's why I2 value is increasing. But এখানে কি হয়ে গেল? অন্বেষা জিনিয়া কোথায় ক্লাসে? এখানে কি হয়ে গেল?
স্যার আছে।
জিনিয়া কোথায়? নেই ক্লাসে? But then in manganese what is it? হ্যাঁ তো উত্তর দিচ্ছিস না নরবরা ধরে। But then what is happening to manganese? Manganese এ কেন আমার ionization enthalpy, second ionization enthalpy in manganese, why all of a sudden it decreased?
Exchange energy gain 0.
Exchange energy loss is 0. In other words, I2 is lower than the previous trend since loss in exchange energy is 0. Can you guys follow that, everyone? Everyone, quickly tell me. Then for iron, it is how much? How much iron it is? Minus 1k, minus 2k for cobalt, minus 3k for nickel, minus 4k it will definitely be for copper also. Can you follow or not? So it is again minus 1k, minus 2k, minus 3k, minus 4k, it will be 0 again. Same logic is again applicable. और को बुझने वाली की पाली ना?
Yes.
Same logic is going to be applied once again here. Correct na? That is the reason it is again following the same pattern. Otherwise, from starting from manganese up to copper, gradually increasing every time. Yes or no, everyone? Tell me, quickly tell me.
Yes. Yes.
So same thing I can write down here. That from manganese to copper, same thing is happening, but all of a sudden in zinc this is happening. Clear for all? Tell me, let me know. That means second ionization energy is much more systematic, or first ionization energy is much more systematic, the variation. Can you tell me that why the first ionization energy change was little, whereas in second ionization energy change is quite drastic?
মানে এখানে second ionization এ Z effective ও বাড়ছে আর মানে exchange energy gain ও কমছে।
Very good. In the first time, during the first ionization enthalpy, Z effective was increasing, but somewhere the exchange energy gain was happening. Somewhere exchange energy gain was 0 also. But then during the second ionization energy, what is it happening? As he told, that as we are moving from left to right, Z effective is increasing and exchange energy is also getting lost. So in both terms stability is decreasing, and that is the reason the second ionization energy, during the second ionization energy, the values are increasing so drastically. Could everyone understand that? Pranjal বুঝতে পারলি? মৈত্রী বুঝতে পারলি? Energy বুঝতে পেরেছিস?
হ্যাঁ স্যার।
What is it saying? The variation of the first ionization enthalpy across the period from scandium to zinc is little, because Z effective is increasing, which is trying to decrease the ionization enthalpy or increase the ionization enthalpy. Everyone, decrease or increase?
Increase.
Tending to increase ionization enthalpy. And same time, exchange energy gain is also mostly increasing. What it will try to do to the exchange ionization energy? It will tend to lower the ionization energy. Am I right or wrong? So collectively what is happening? The ionization energy is not increasing or varying much. Collectively, the first ionization energy does not vary much because two opposite factors are happening simultaneously. But when we are talking about second ionization energy, but when we look into the second ionization energy, then from scandium to zinc, both Z effective is increasing, that is tending to increase the second ionization enthalpy value, also exchange energy stability is getting lost, that is tending to increase the ionization energy. That's why I2 values vary much more than I1 values. मौसम এটা বুঝতে পারলি কি পারলি না? হ্যাঁ বল। पक्का? Okay. Now if I look at the third ionization enthalpy value. Oh, achha, sorry. Now finally if I look at the third now you think and tell me, during the third ionization energy process or third ionization process, what should happen to the variation of the ionization enthalpy values? What is your expectation? What do you think? কি মনে হয় ঐশিক, যখন থার্ড আয়নাইজেশন এনার্জির ভ্যারিয়েশন দেখব তখন আমার আয়নাইজেশন এনথালপির ভ্যালুস গুলো সেকেন্ড আয়নাইজেশন এনথালপির মতনই এতটা ড্রাস্টিক চেঞ্জ হবে, নাকি ফার্স্ট আয়নাইজেশন এনথালপির মতনই কম চেঞ্জ হবে, নাকি আরো বেশি কিছু চেঞ্জ হবে, নাকি আমার অ্যাব্রাপ্ট চেঞ্জ হবে, নাকি খুবই ইররেগুলার চেঞ্জ হবে? হোয়াট ডু ইউ সাসপেক্ট? অনির্বাণ, সাগরিকা, everybody else, অন্বেষা মিশ্র, সাহা, অর্চিতা, ডেকা, অরিজিৎ।
ওখানেও মানে ড্রাস্টিক চেঞ্জ হবে, মানে বাড়বে অনেক বেশি ভ্যালুস করে বাড়বে।
ভেবে বলছিস না দেখে বলছিস?
দেখবো কোথায়, না দেখিনি আমি।
ওকে, now if I look at the data, so 2393, obviously third ionization energy will have higher value than second ionization energy. 2657, 2833, 2990 3260 2962 3243. Yeah, so large values. 3402 3556 3857. So what are you observing? Increased, 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 decreased, then again increasing, 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 increasing. Can you follow? Tell me everyone, can you follow? Come on, tell me observation, just the observation you tell. Throughout it is happening what? Throughout the series, what is it happening? And is it some anomalous that it is increasing?
No.
That should be happening only, right or wrong? That only should happen, yes or no?
Yes, sir.
So Z effective increases, exchange energy gain decreases, thus third ionization energy increases. The same thing I am attaching here, but then what went opposite or different for iron? Who can tell? We have already done it. Ranjal, what went different with iron?
So, 0.
You see, somewhere we have done. Here you see iron plus 2 to iron plus 3, it is zero loss of exchange energy. For the remaining ones, during the plus 3 formation, it was a negative exchange energy gain. That means exchange energy was losing, exchange energy stability was getting lost. But from iron plus 2 to iron plus 3, the loss in exchange energy is zero. Could everyone understand that part?
Yes, sir.
Here, loss in exchange energy upon Fe plus 2 to Ap plus 3 formation is zero. That's why Fe plus 2 has lesser I3 value than the adjacent elements. Tell me, till here are we clear or not? Should I go up to কোন পেজে যাব? এখানে যাব? Oh. Now everyone get out your take your NCERT textbook and come to this ionization enthalpies page. Please do it fast. সবাই নিজেদের NCERT আয়নাইজেশন এনথালপিস পেজটাতে আসবে তাড়াতাড়ি। और को डन. গাঙ্গুলি তো নেই না, গাঙ্গুলি খুব ভালো রিডিং করে রে. Okay, Orko then take it out. Here, everyone, please open your own NCERT textbooks. Start, Orko.
There is an increase in ionization enthalpy along each series of the transition elements from left to right due to an increase in nuclear charge, which accompanies the filling of the inner d orbitals. Table 8.2 is the values of the first
তুই নিজের বই থেকে পড় না, তোর বই কোথায়? তুই নিজের বই থেকে পড়লে মোর কমফোর্টেবলি পড়বি. স্বরূপ কার কাছে আছে বই? হাতের কাছে কার কাছে আছে? তাড়াতাড়ি চলো.
Table 8.2 is the values of the first ionization enthalpy of the first series of transition elements. These values show that the successive enthalpies of these elements do not increase as quickly as in the case of non-transition elements. The variation in ionization enthalpy along a series of transition elements is much less in comparison to the variation along a period of non-transition elements. The first ionization enthalpy in general increases, but the magnitude of increase in the second and third ionization enthalpies for the successive elements is much higher along a series.
Now highlight this one. This now we only proved no. The first ionization enthalpy in general increases, but the magnitude of increase in the second and third ionization enthalpies for the successive element is much higher along the series. Why did we tell that? Because of loss in exchange energy stability, right or wrong everyone? Satyajit, correct na?
Correct.
Then continue.
The regular trend in the first ionization enthalpy of the metal substrate series of little control significance can be accounted for by considering that the removal of one electron
No, this one. Highlight. Arey, oh, Rubbe. Highlight this one by considering that the removal of one electron alters the relative energies of 4s and 3d orbitals. What do you mean by that? Tell, what is the meaning of it? What is NCERT giving hint towards? That means first, now you see why are they telling that in the first line itself, that first ionization enthalpy though of little chemical importance, because almost most of the d block elements, they are forming +2 and above oxidation number. So +2 and above oxidation number means first ionization enthalpy is not of much of importance, but still without understanding that we cannot go further for the successive ionization enthalpies. So they are giving the hint towards that once the electron is removed from the 4s, the remaining 4s electron should be submerged with which one? D orbital. Can you understand everyone? Continue.
We have learned that when d block elements form ions, ns electrons are lost before n minus 1 d electrons. As we move along in the 3D series, we see that temperature increases flux carry out the same, but electrons head to the orbital of inner substance, that is p orbitals. These trailing electrons shield these bonus electrons to make them somewhat more effectively than the outer shell electrons field.
This one we just now told. That the 3d electrons should shield the 4s electrons from the increasing nuclear charge somewhat more effectively than the outer shell electrons can shield one another. That means 4s electrons shielding 4s electrons, 3d electrons will shield 4s electrons more effectively. In the beginning that we told that. Continue.
Therefore, the atomic delay increases less rapidly. Thus, ionization energies increase only in the 3D series. or more highly charged ions have DN configurations with no force electrons. A general trend of increasing values of second IT is expected as the effective nuclear charge increases, because one d electron does not shield another electron from the influence of nuclear charge, because the orbitals differ in direction.
Correct. Z effective is increasing from left to right, that they are trying to say.
However, the trend of steady increase in second and third IP.
Second and third IP. Right, read it very carefully. Better you can note it also. But steady increase in I2 of manganese and I3 of iron. Continue.
The trend of steady increase in second and third IP based on the formation of Mn2 plus and Mn3 plus respectively. In both the cases, ions have D5 configuration. Similar breaks occur at corresponding intervals in the latter transition series.
Now what is the meaning? Just now we studied. Just a minute. What is the meaning of this last statement? You see, third ionization enthalpy, what was that saying? What was the line they were telling? Mention it. That the trend in the steady. হ্যাঁ তেরি কি তোর নামে এত তখন থেকে শুধু ঢুকে অ্যাড হতে চাইছি না, মানে বোধহয় আমি 500 বার শুধু রিজেক্ট করে যাচ্ছি, মাথা গোল যাচ্ছে আমার। তোর নামেই হয় এটা, এটা নিজ্ঞাত রিক করে, আমি শিওর নাও। নয় শুভদীপ নয় রিক, দুজনের মধ্যে একজন করছে কেউ। Now what is it that read the line everyone, that however the trend of steady increase in second and third ionization enthalpies breaks for the formation of Mn plus 2 and Fe plus 3 respectively. You see, it was steady increase in the third ionization enthalpy, but that trend got broken while the formation of Fe plus 3. Why did that happen? Because of the loss, no loss of exchange energy. Similar thing happened for, you see, in manganese. During the second ionization enthalpy, it was a steady increase from scandium to chromium, but then it again the trend got dropped in Mn because there was no loss in exchange energy in manganese. In this way, in NCERT it is written. Can you follow everyone?
Yes, sir.
Now continue. The three terms responsible for the values of ionization enthalpy are, here you make it 1, 2, 3. Attraction of each electron towards nucleus, that is Z effective. Repulsion between the electrons, that is pairing energy, and the exchange energy, very much noted. First, Z effective. Second, pairing energy. Third, exchange energy. Can you follow that? What is it saying? Swarnali, can you go for it? What is it saying? Come on, fast, quickly. Swarnali, go, leave it.
আমি না আমার ওল্ড এনসিইআরটি কোথাও খুঁজে পাচ্ছি না।
আর খুঁজে পেতে হবে না তোকে, ইয়ে কে
আমার এখানে লেখাটা অন্য
মেরেছে, তাহলে থাক। লতা, গো অ্যাহেড, কাম ফাস্ট। রিমঝিম, ঘুমোচ্ছে বোধহয় না? কালকে স্কুলে আয়, তোদের আমি গলা টিপে মেরে মারবো এবার। স্বরূপা, গো অ্যাহেড।
Exchange energy is responsible
জোরে খাসনি নাকি দুপুরবেলা জোরে কেমন
মাইক থেকে শোনা যাবে না, ওর থেকে আমি ভালো।
আচ্ছা তুই পড় বাবা মা তুই পড় হ্যাঁ
আমি বলতে পারি।
আচ্ছা ঠিক আছে
হ্যাঁ, বলছো না কেন?
ও মা, তোর বলে না?
এ এ এ এ এ তোরা
স্যার আপনি পড়ুন।
হ্যাঁ তো ঐশিক পড় থেকে
Yes, sir, নাই
আমি
নাই।
পারি না স্যার।
ইডিয়েটস লতা
পড়ছি।
হ্যাঁ
Sir,
ঐশিক
sir.
Exchange energy is responsible for the stabilization of the energy state. Exchange energy is approximately proportional to the total
Underline,
number of
underline.
pairs of parallel spins in the degenerate orbitals. When several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to the maximum possible extent of single occupation of orbital and parallel spins. Hund's rule. The loss of exchange energy increases the stability. As the stability increases, the ionization becomes more difficult. There is no loss of exchange energy at the D6 configuration. Mn plus has 3d5 4s1 configuration, and configuration of Cr plus is d5. Therefore, ionization enthalpy of Mn plus is lower than Cr plus. In the same way, Fe2 plus has d6 configuration and Mn2 plus has 3d5 configuration. Hence, ionization enthalpy of Fe2 plus is lower than the Mn2 plus. In other words, we can say that the third ionization enthalpy of Fe is lower than that of Mn.
now you stop and think so difficult language they have used Orko correct or not but what we have studied that only they have described or not throughout what we have been studying from the morning I was trying to establish this exchange energy point of view that only is described only in a small paragraph of NCERT can you understand this exchange energy thing Pranjal মাথায় ঢুকেছে কি ঢোকেনি
Yes, sir.
it is beautiful go ahead
The lowest common oxidation states of these metals is +2.
highlight this
To form the Mn2 plus ions from the gaseous atoms, the sum of the first and second ionization enthalpy is required. In addition to the enthalpy of atomization, the dominant
highlight this one what is required what is total required I always look for the chemical reaction in aqueous medium now to get in aqueous medium first solid to gas to plus 1 ion plus 1 to plus 2 ion then that plus 2 ion needs to be dissolved into the aqueous medium so what is it saying the sum of the first and second ionization enthalpy in addition to the atomization enthalpy continue
The dominant term is the second ionization enthalpy, which shows usually high values of Cr and Cu, whereas Mn plus ions have D5 and D10 configurations respectively. The value of for Zn is correspondingly low as the ionization causes the removal of 1,4s electrons, which results in the formation of stable D10 configuration. The trend in the third ionization enthalpies is not complicated by the 4s orbital factor and shows the greater difficulty of removing an electron from the D5 Mn2 plus and D10 Zn2 plus ions. In general, the third ionization enthalpies are quite high. Also, the high values for the third ionization enthalpies of copper, nickel and zinc indicate why it is difficult to obtain oxidation state greater than 2 for these elements.
can you understand everyone can you understand
Yes, sir.
শ্যামাশ্রী নেহা মৌসম অন্বেষ
হ্যাঁ, স্যার।
জিনিয়া তোরা
Yes, sir. হ্যাঁ,
তোরা
স্যার।
তোরা আগে বুঝতে পেরেছিস কিনা বল
হ্যাঁ, স্যার। হ্যাঁ, স্যার।
পাক্কা
হ্যাঁ, স্যার। হ্যাঁ।
clear for all I guess till now clear for all everyone till here chalo
Yes, sir.
so this whole context which is written here we have discussed in notes see in notes Tell. The number of valence electrons present in the metal among chromium, cobalt, iron, nickel, which has the lowest enthalpy of atomization. Which one will have the lowest atomization enthalpy? First, from left to right, increasing, then it decreased. So which one should have the lowest atomization enthalpy, everyone? But there is a small catch in this, but you have to understand that. This is something which is very much, what should I say, typical value, typical question, which is unlikely to be answered properly because it is very much trend based.
Iron, right?
See,
Carbon, nickel, highest which?
it is directly trend based question being asked.
Wait, iron. Lowest.
Among these, iron, cobalt, nickel, and which one else? Chromium.
Yeah.
Chromium is the lowest in this case because first you are increasing, no. Chromium is also given in that question, no. So what is the graph saying? If I look at the graph, it is first increasing. So here it is, what is it there? Titanium, vanadium, chromium. Somewhere here it will come, and in terms of atomization enthalpy, vanadium will have the highest value. It is clearly given in such a way so that if you are not revise this thing, you will not be able to answer this question. Not possible. It is likely you will do mistake. It is very much likely you will do mistake. Everyone will do mistake. So they are technically they are talking about chromium. Technically they are talking about chromium. So valence number of electrons, it is 6. 3d5, 4s1. Okay. Similar question. चलो. A transition metal M among scandium, titanium, vanadium, chromium, manganese, iron. दुनिया राज्य शब्द दे दिए थे. Scandium, titanium, vanadium, chromium, manganese, iron. Left to right, up to iron, all are given. Has the highest second ionization enthalpy. Which one is that? I2. Highest second ionization enthalpy. How to do that? Just now we have done that. Without just going for random guess, we have to draw the configuration. We have to write the configuration. Scandium, it is 3d1 4s2, 3d2 4s2,
Do it, tell me man.
3d3 4s2, 3d5 4s1, 3d5 4s2, 3d6 4s2. So which one should have the highest second ionization enthalpy value? Which one? Chromium. Because during the second ionization, chromium will lose its half-filled configuration. Correct or not, everyone?
Yes, sir.
So M plus, that means chromium plus, what is its electronic configuration? 3d5. So spin only magnetic moment value dash Bm. What is the formula? Root under n into n plus 2 boromagneton. Correct or not, everyone? So 5 into 5 plus 2, that means it will come approximately around root 35, no? Which is approximately nearest integer 6. Tell me. Tell me, everyone. Shavarika, Oishik, Anjol, Urchita, Aryan, Arjudeep, Deka, Devjit, everyone.
Yes, sir.
How much is it
Yes,
coming?
sir.
Nearest integer? The 3. These type of questions are very much easy to do. Arrange the following elements in increasing order of number of unpaired electrons. You have to draw the electronic configuration. Based on that, you can do it. Then oxidation number you can find out for these. From there, you can find out the spin only magnetic moment value. Unpaired electrons you can calculate. Same here also, unpaired electrons you can find out. From there, magnetic moment value you can find out. Okay, till here, everyone. Just let me know quickly.
Yes, sir.
Okay, now we are going to get into the part of standard reduction potential or electrode potential. A E naught M2 plus M. Now you see, what are we supposed to do is the one that we were trying to do in the before the break. Metal solid, first that need to be converted into metal gas by applying enthalpy of standard enthalpy of atomization. Then by applying first ionization enthalpy, we will be able to get the M plus gas. By then applying the second ionization enthalpy, we get M2 plus gas. By then applying hydration enthalpy, standard hydration enthalpy, we get M plus 2 aqueous. And if I wish to do the whole thing in one step, try to recall, we did in thermodynamics the Hess's law. Remember, everyone? Jinia, mona parudu?
Yes, sir.
So delta H total. What are we supposed to do then? This plus this plus this plus this. Correct, no, everyone?
Yes, sir.
Correct, okay. this value comes out to be positive versus if this value comes out to be negative. If this value comes out to be positive, then it is technically energetically favorable or unfavorable? Moitri. Can everyone get it?
Unfavorable. Yes, sir.
Correct. And it is favorable. Now you see, the enthalpy of atomization, if I look at it, the first transition series only I'm focusing, 3D series. For the 3D series, enthalpy of atomization more or less, as the graph permits, enthalpy of atomization, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. So as the graph is suggesting to us that what is supposed to happen initially, it will keep on increasing. Vanadium will have the highest enthalpy of atomization, then chromium, and up to like this, and then zinc will have the lowest value. A qualitative diagram, or merely a qualitative diagram. That if I look at the first ionization enthalpy plus second ionization enthalpy together, then we see that first ionization enthalpy is very much irregular. Sometimes it is increasing, sometimes it is decreasing. First ionization enthalpy, here only we have plotted that some more or less it is increasing and it is becoming maximum first at the iron, then cobalt, nickel, it is decreasing, then it is again becoming maximum at the zinc level. That we have experienced in the very beginning. Can you follow? And সেটাই যখন আমরা second ionization enthalpy দেখছি, what is it happening? Scandium through chromium, it is gradually increasing. Only at manganese, second ionization enthalpy is dropping down because of no loss in exchange energy. And afterwards from iron to zinc, again it is increasing, and zinc again it is decreasing because of no loss in exchange energy. Correct everyone till now?
Yes, sir.
So both the parameters collectively is making a very much anomalous trend. That means sometimes atomization enthalpy is increasing, sometimes ionization enthalpy is increasing then decreasing, second ionization enthalpy increasing then decreasing. Hydration enthalpy also has its own irregular pattern of values. So technically it is not possible for us to predict the exact order of the standard reduction potential value. It is not possible to do that. What max we can do is, we take the help of table 4 in NCERT. I would ask you all to open the table. If we look at these values, then we find that these all values are technically the E0 SRP values. This is the SRP value, reduction potential value. There we will see that what is it happening, only at the copper level we can see that it is positive SRP. Now how can we explain, let's say here two data are given to us. What if the data are not given to us? Then how do I explain the positive SRP value theoretically without knowing the data for copper? How do I explain this? Right now the data is given, but real time data is not given. Obviously I don't also remember the data. So how do I explain the, what is that called, positive SRP value?
Positive means unfavorable.
That is true.
And so we can take help of the exchange values as it's decreasing. So
Sure, obviously yes, but then do it properly, tell it, explain it properly.
to balance the checkbook.
Everyone do it. Do it. Is my question making sense to all of you? That if it is asking how to explain the positive standard reduction potential value of copper, the meaning of this is that copper plus 2 Readly wants to convert into copper. That means copper plus 2 has a high tendency to undergo reduction. That is why copper plus 2 is an oxidizing agent. Whereas the other metals we can see is capable of acting as a reducing agent. Can you follow that? That we have studied in electrochemistry. But that now I'm asking, the electrochemical data, can we support that from thermochemical data set as well? Now obviously if the data set is provided to us, it becomes very easy for us to explain that phenomena. But my question is, without data, theoretically, how to explain this thing? Our question is very busy.
Yes, sir.
Tell me, how to explain the high positive SRP value of Mishra Guzrati's question done, copper plus 2 copper,
Yes, sir.
without data. Without data. That means, first of all, we have to understand that it refers that from copper to copper plus 2, delta G naught must be positive. Because copper plus 2 to copper, delta G naught is negative. It is aqueous, it is solid. For this, delta G naught is definitely negative. That we can see from this value, because delta G naught equals to minus NF E naught. If E naught is positive, delta G naught will be negative. Orko, can you follow? Now delta G naught positive, how can you explain that? Theoretically. Theoretically, how can you explain? Without knowing the data, because obviously during the examination time we will not have the data set, maybe we will not have the data set provided. The only thing that we can expect or to explain that is that high value of the sum of first and second ionization enthalpy. If the first and second ionization enthalpy of copper is very high, because see, atomization enthalpy of copper, because it is in the lower end, in the terminal part, will be low. So from solid to gas it will easily be formed. But ionization enthalpy value also from left to right increases. So for copper, the first two ionization enthalpy values collectively will be very high. Can you guys follow?
Yes, sir.
And definitely that high ionization enthalpy value should not get compensated by hydration enthalpy. Can you follow? If the hydration enthalpy can compensate, for example, let's see, You do this, we do this addition, let's say. Let's say we do this addition. Let's say we are doing this for
exactly.
Exactly. Exactly. For example, let's say titanium. For example, just randomly. So it is 515 plus 650 plus 1414. Correct or not? Now it is minus 1895. It is now it is, sir, it is also coming positive only, but yes, not this hydration enthalpy and these data. Entropy data is also important, because we know that finally if I have to say something when predicting the delta G naught, I need delta H naught minus T delta S naught. Then maybe delta S naught is also playing an important role, which data is not provided in NCERT. So mostly I can say that for copper, possibly the overall copper to copper plus 2 transformation is highly endothermic, where the hydration enthalpy is largely incapable of compensating the first two ionization enthalpy values. So how am I explaining this? Copper to copper plus 2 perhaps have very high value of first and second ionization enthalpy sum that is not at all compensated by hydration enthalpy. Thus, copper solid to copper plus 2 aqueous formation is thermodynamically unfavorable. Hence, E naught Cu plus 2 Cu, because copper plus 2 is not so stable, so it will have positive SRP. Can you guys tell me, have you understood or not?
Yes, sir.
Okay, if you have understood, then if I take this question, let's say, how do you explain this? Can you see it? They are asking to explain this, correct? No? So you see, from vanadium to chromium to manganese to iron to cobalt to nickel to copper. Mostly the whole spectrum is given. What is happening to the SRP values? Vanadium to chromium, it is increasing or decreasing? Increasing. So from here to here, SRP we are looking at it. SRP from vanadium to chromium increases, but from chromium to manganese decreases. Manganese to iron increases. Iron to cobalt increases. Cobalt to nickel increases, and nickel to copper increases. But then why A naught chromium plus 2 chromium to E naught Mn plus 2 Mn decreases? Why? This is the only irregularity. No, what is the reason behind the irregularity?
যেটা আমরা সেই I2 পড়ছিলাম ওই নো লস এক্সচেঞ্জ
हाँ हाँ explain them, explain using that and explain that and explain this, using that explain this.
Manganese no loss of exchange energy, so ionization enthalpy is more than chromium.
No loss in I mean, see, here we are trying to establish manganese to manganese plus 2 versus chromium to chromium plus 2. Which one will have
energy left
correct, no?
as compared to Cr2+.
Here I2 value is more, comparatively I2 value will be low, because for manganese to manganese 2 plus, if I look at it overall, then manganese plus থেকে manganese plus 2 যখন তৈরি হবে তখন আমার হাফ ফিল্ড কনফিগারেশন লস হবে, whereas in chromium plus থেকে chromium plus 2 যখন হবে তখন হাফ ফিল্ড কনফিগারেশনে লস নেই. That is the reason chromium to chromium plus 2 is easy to form. Can you follow, everyone? Tell me. Tell me.
Yes, sir.
Acha. So basically, low value of E naught M2 plus M for vanadium and manganese. How do I explain? Low value of this means what? It wants to form the M2 plus or it does not want to form the M2 plus. SRP এর কম ভ্যালু মানেটা কি? সে M plus 2 থেকে M এ যেতে চাইছে না M থেকে M2 plus এ যেতে চাইছে? That means M থেকে M2 plus is favorable. Now why is that happening? Most likely যে delta H atomization plus I1 plus I2
এখানে ওই তোমার ওইটা হাইড্রেশন এনার্জি কম্পেনসেট করে দিই
and hydration enthalpy compensates. Maybe for vanadium and manganese, the enthalpy of atomization, first and second ionization enthalpy, they are collectively smaller in value, and hydration enthalpy collectively is larger in value. So that overall M to M2 plus, that means vanadium to vanadium 2 plus, manganese to manganese 2 plus, they are favorable to form. Can we all understand? Tell me quickly. Quickly.
Yes, sir.
Okay. So
Yes, sir.
আমি এটাকে শেষ করছি ক্লাসটাকে, বাট আমি এর সাথে একটা ফাইল মানে নোট কয়েকটা অ্যাটাচ করে দিচ্ছি। এর সাথে আমি কয়েকটা নোট অ্যাটাচ করে দিচ্ছি। এটাকে আমি পড়তে বলছি, এটার জন্য আমি আলাদা করে একটা ক্লাস নেব। হ্যাঁ, এটার জন্য মানে মেজরিটি অফ দ্য বিগ চাঙ্ক সাকসেসফুলি ডান। এরপরে আমি সবকটাকে কোয়েশ্চেন আনসার ফরম্যাটে ডিসকাস করে দিয়েছি। অক্সিডেশন স্টেটস কিভাবে আমরা এক্সপ্লেন করতে পারি, and তারপরে তার এগেইনস্টে questions. Why does oxidation state of transition metals vary by 1 unit? For p block elements, the stability of lower oxidation state increases down the group, inert pair effect, but that of d block element increases down the group. Why? Then stability of higher oxidation state by the halide and oxide, how do we explain that? In the form of question. Then assertion, reason, form, questions. I have given the whole context out of it in the form of a question, so that if you read it you can understand very properly and clearly. And afterwards, this is I have attached along with it that we have to take separately, that is some important compounds of transition elements, potassium dichromate and potassium permanganate. So for that we will take a separate class also. Okay. Okay then, everyone, hopefully understood everyone.
Yes, sir.
ठीक है ना?
Yes.
It's a big chapter. Yes, it's